Today I'm going to give you explanations about the project of this project in this course. And we already discussed it a couple of times, but as you see, we have a highway. Currently, this highway is under construction, and you know that sometimes the highways are crossing rivers or streams, and whenever highways are crossing the streams or rivers, we have to put a hydraulic structure such as bridge or culvert, so that this will help water to flow from one side to another. This is required for the safety of the people and for the stability of the highway. Otherwise, water accumulates behind the road, because road works like a small dam, and water overtops the road, and whenever it overtops the road, it breaks the road, the road collapses. Okay, of course not in every overtopping road collapse. If there are some small scale overtopping, highway might not be collapsed, but if the flow amount is very high, and it continues for a long time, eventually it breaks the highway. So there are lots of examples around the world that we are experiencing this, because it's not, we cannot say that you are going to put a culvert and this will protect your highway for every condition or under every condition, because this is a natural event. Rainfall is a natural event. So we are taking certain amount of risk and designing these kind of structures. So risk can never be zero. We have to lower the risk, but always there is a risk of failure. Okay, even if this risk is very low, it might happen in the future. Okay, so first thing is, whenever you see a culvert is not working and the bridge, water is overtopping the bridge, overtopping the culvert, this doesn't mean that it is a misdesign. Okay, remember this. It doesn't mean that it is a misdesign. There is a mistake in design, or design is not right. This could be, or definitely this could be a misdesign, but this could also be very, very extreme event, that extreme rainfall event, that you actually didn't design your structure for that much extreme rainfall event. Consider maybe it's like earthquake design, because we are designing buildings according to certain level of earthquake. But if very, very extreme earthquake event happens, even the building which is designed for acceptable earthquake conditions can collapse or can damage. Okay, so this is like that. Let me explain this from the very beginning. As you see, like in this example, we have a culvert, but on the other hand, we have a dam close to the culvert. So maybe because of a very high rainfall, this dam breaks and huge amount of water flows here, and your culvert cannot be enough for letting flow from one side to another. If you want to consider all these risks into consideration, if you want to take all these into consideration, in this case, your culvert size will be very, very large. And in this case, you will spend maybe double, maybe 3 times more money to construct this culvert. This is not, and on the other hand, an engineering point of view. This is not an engineering approach, because in engineering approach, we are trying to find the economical solution by taking acceptable risks. Okay, so this is the case in our project. So culvert is going to be designed. Okay, so when they are designing the culvert, what they need a flow, design flow. Okay, so your job here in engineering hydrology is to find what is the design discharge for that culvert. Okay, so first thing that you are going to do to decide about the design rainfall, because the flow is not continuous here. So you don't have continuous flowing. If it is a river that is flowing continuously, in this case, you directly use flow data. But if the flow is not continuous, it's not flowing every day, it's just some seasonal flowings are happening, and there are no flow data, flow measurements are not done on that stream or river. In this case, we are using hydrologic analysis and design. What is hydrologic analysis and design? You look at the rainfall data and you convert rainfall data into flow. So we have seen this in detail in the course, okay? How we can convert rainfall into runoff, okay? We did this in detail. So here we are going to do exactly the same thing. But in order to change rainfall into flow at the exit of the basin, you have to know in some characteristics of the basin. Okay, so first of all, you have to define the basin. You should find the basin, draw the basin, and then you are going to use different characteristics of the basin. Of course, this depends on which method you are going to use, because this is called rainfall runoff application or rainfall runoff model. Okay, we are converting rainfall into runoff. Which method you are going to use, and every method has different parameters, different basin characteristics are required for every method. Then after decision of the method, you are going to see which parameters are required, and you have to calculate or measure these parameters from your basin. In this case, you will have a basin information, and using the basin information, basin data and rainfall data, you will be able to calculate flow at the exit of the basin. And this flow is actually will be your design discharge. The peak value, of course, the maximum, because the flow is not constant. Whenever rain starts, flow is not being constant. Rain starts, water starts flowing on the surfaces, then this water finally reaches to the exit, but the rain continues depending on rainfall event. In other words, the hiatograph of the rainfall event, you know that part of it is infiltrating underground. So we have to find the excess rainfall. We have to find the runoff part of the rainfall event. And this runoff part will be multiplied with the, or will be combined with the basin characteristics. Okay, so here in this, it is mentioned, it is given to you that in order, we have also seen, let me tell you this one, we have also seen the statistical methods in hydrology. and we decide, we learn how we can calculate the rainfall event or stream flow event with different return periods. Okay, like 100-year return period. The return period, as you understand from the name, it is the duration that this kind of event in average comes again, happens again. Okay, so that's we call it return period or recurrence interval, we also call it. Okay, and if you are designing for 100-year return period, 50-year return period, 25-year return period, maybe 500 return period, these rainfall values with different return periods are of course changing. When you are increasing the return period, you also increase the rainfall event, because it is very extreme cases when you are increasing the data, rainfall data. You are getting to extreme cases, and these extreme cases are happening more rarely. Okay, so 100-year event rainfall is always higher than 50-year event. Okay, or 500-year event is always larger than 100-year event. So here, of course, which return period will be used depends on the regulations and specifications of that country, of that region. This could be different from the region to region or state to state, under federal conditions, for example, or from municipality to municipality. This could be different. Because when you are increasing the design return period, this means you are increasing the rainfall data or stream flow data. In other words, this means you are increasing the dimension of hydraulic structure, which means you are going to spend more money to design, to construct this culvert or this bridge. Okay, so these are all related to each other. So, but on the other hand, if you are increasing the return period, you are decreasing the risk of failure is decreasing, because the lifetime of the project and the return period, these are two parameters to calculate the risk of the hydraulic structure. In this case here, of course, another criteria in the decision of design return period is the importance of that place or of that structure, such as, is it a highway? Is it a first-class highway? Lots of people are driving on this highway. Traffic is very high on that highway. So in this case, you are increasing the return period for design. But if it is a culvert which is located on a very small scale traffic, in this case, you can take more risk under this condition. Okay, so this is also another important thing. So a rainfall station given to you, which is close to catchment area, because as you see from this picture, you can easily see the river system. Actually, you see how the rivers are coming, and you have because Google Earth gives us an opportunity, even if you don't have topographic maps, Google Earth gives us opportunity to draw or to see three-dimensional view of a basin, of an area. So as you see from this picture, I see that this part is top of the hills, and I also see that this part is top of the hills, and I see the river system, one from here, which is coming actually from this area, and another river network is coming from this direction. As you see, this goes up to here. So my catchment area goes up to the top of the mountains and comes like that. So since there is a good catchment area, that is the main reason that they constructed this dam here, because the decision of the location of the dams are very critical. You are trying to put it on a location that you are collecting more water. Okay, so here, since because of the culvert, so since you have a reservoir before the culvert, we have to let water to get into the reservoir first. Then from the reservoir, a certain amount of water will be collected in the reservoir. It will be stored in the reservoir. This will decrease the peak discharge, which is our next topic, which is called flood routing. This is our next topic in our lecture notes. And then we have to find the exit hydrograph. Okay, input hydrograph. Then using the reservoir characteristics, we will have exit hydrograph. Okay, so here we see that we need to know basin characteristics. On the other hand, we need to know reservoir characteristics. When we say reservoir characteristics, what these are? Height, volume change. Whenever 1 meter water is collected, how much volume of water it makes. How, and whenever certain flow amount is getting in, how much is getting out. You can, because you know in the reservoirs you have a outflow structure such as spillways from the top of the dam or bottom outlets from the bottom of the dam. You let water to flow down. Using these characteristics, we will be able to calculate what will be the exit flow from the reservoir, and this peak value of this exit flow, because when I say exit flow, but exit flow is changing by time. And then we are calculating the peak flow coming to culvert location, and this will be our design discharge. Okay, so rainfall station is given to you, rainfall data is given to you. So first thing is to find design rainfall. Okay, we are going to find the design rainfall and then convert this design rainfall into design discharge. But you know, in statistics chapter, we have seen 4 probability distributions. One of them is normal distribution, other one is log normal, person type 3, and extreme value. These 4 distributions, as you see here, is usually one of those 4 distribution fits your peak data well. What is peak data? This is the maximum daily observed data along the year. Okay, because 365 days we are taking the maximum daily rainfall for that particular year. And every year we take the maximum, then we are getting a set of data, yearly data, but yearly data represents daily rainfall. Every year in one day, maximum rainfall that we have observed. Okay, but when you are considering 4 different probability distributions, 4 of them might give you 4 different results. So here, which one will be selected depends on goodness of fit test. Okay, so whichever distribution fits your data better, you will select the results of that distribution. Okay, if normal distribution is not fitting your data well, in other words, your data is not normally distributed, you shouldn't use normal distribution to find to find the design rainfall from the data. Okay, so it should be the one that with a good fit. So we have to apply goodness of fit test. There are 2 goodness of fit tests. There are a number of tests actually, but 2 of them are very commonly used one in hydrology. One of them is the chi-square test, and other one is Kolmogorov-Smirnov test. Okay, so this actually we haven't seen this topic, goodness of fit test is not seen. Maybe some of you, if you have already taken Probability and Statistics in Civil Engineering, CVE 303 course, most probably you have seen this there. But if you didn't take that course, since it is not a prerequisite of hydrology, maybe you didn't take it. In this case, we are going to, you will see it. I will explain it in detail. Okay, so you will apply the goodness of fit test and then decide which one, which distribution fits better. Using that distribution, you are going to calculate P over P100, let's say 100-year return period will be calculated. Using frequency analysis, this will be done, but this will be just one value in your hand. You have to convert this into hourly distribution. So in order to change this, convert this into hourly distribution, you need to know in that region if how is the daily rainfall characteristics or daily rainfall distributions are changing. What we mean daily rainfall distribution, when you are obtaining a daily rainfall data, what percent of this amount comes in first hour, what percent comes in second hour, what percent comes in third hour? Because when we say daily means this rainfall event continues for 24 hours and it is collected at the end of 24 hours. Maybe the event is not as long as 24 hours, maybe it is shorter, but we are all considering all the rainfall events and try to find average distribution. For example, in Boğazköy station, this is given to you, and we see that in the first 1 hour, around 20% of rainfall daily rainfall is obtained in one hour. When we look at the second hour, another 18 to 20% is happening in the second hour. This shows us that in Cyprus or in Boğazköy station, rainfall events are not going up to 24 hours. Actually, rainfall events are short and majority of rainfall is obtained in first couple of hours of the rainfall event. So once you get the frequency analysis, you calculate the design rainfall, which be careful with the units always helps you. You are going to find from the goodness of fit test P100 year, but this is a daily rainfall and it is happening in the unit is in millimeter per day, but we have to convert it millimeter per hour, which is rainfall intensity. Okay, and once you convert it to hourly periods, which actually is also called heatograph, we have to find what is the infiltration capacity of that. So what is the excess rainfall? Because when it is raining on the surface, as you see, it's a very rural area, significant amount of water is actually infiltrated. Okay, and using this infiltration, actually water is not running at the surface, but the remaining part after infiltration, remaining part is flowing at the surface. So we have to figure out what is the runoff part of a rainfall event. So that's why excess rainfall is important. Excess rainfall here means runoff. Runoff means the water which is running at the surface and going to the river or the reservoir. Okay, so here you are going to use Horton method to calculate the infiltration capacities. What it is assumed that the soil type is silty clay loam, soil type of a basin. Okay, if you look at the soil type of a basin, actually part of it goes up to mountains, but part of it is on the agricultural area. So you can, using this soil characteristics, because the silty clay loam is a soil characteristic, and actually soil characteristics of every country is more or less developed, because uh, every country wants to know what is the quality of their soil and which parts should be allocated for agricultural activities, which parts should be used for urbanization. Like if the soil characteristic is very, it's not rich, it's very low, in terms of quality. In this case, maybe it will be good to make your buildings or urbanizations, maybe factories or something like that, on that kind of soil, not a good agricultural quality soil, because we need these soils, this kind of lands, agricultural lands, for future generation to practice and to produce crops and be able to survive in the world. Okay, so silty clay loam, you know what we said? We said that use Horton method, but Horton method, if you look at the equation of Horton method, you will see there are coefficients in the Horton method. F initial, in other words, infiltration capacity initial, infiltration capacity final. These are, and there is a K value. These are all given in a table. So if you look at your lecture notes, you will see that if your soil is silty clay loam, the initial infiltration, final infiltration, and K factor, they are all defined in the table. So you are going to get it from the table directly, and you will generate your Horton infiltration equation. And according to the equation, you will decide what is the excess rainfall. Okay, because let me quickly draw it here. If you have a, let's say, hiatograph like this is maybe observed rainfall event, intensity versus time. Okay, and you know time is maybe 0, 1, 2, 3, goes like this. So you have to calculate what is, what is infiltration capacity when T is equal to 0. Because if you look at the infiltration, Horton infiltration equation, this equation has T, which is T is the variable, T will change, and the other constants are coming according to soil type. Okay, so when T is 0, you will find F, for, which is infiltration. When T is equal to 1, again you will find. When T is equal to 2, again you will find. When T is equal to 3, again you are going to find. Okay, and you are actually, if you connect those points, the area below is your infiltration, but area above is your runoff. Okay, but in order to make it simplified, and don't use integration, because you know using the integration you can calculate the area under the curve. So we can convert this curve, as you see these blue lines, the blue points, if you connect it, you make a curve. But instead of making a curve, we are doing approximation, like what is the average value between those two. And another approximation, and another approximation we are doing. So if you do approximation, like the value of F at T is equal to 0, and value of infiltration F when T is equal to 1. And if you take the average of those, you get this line. Okay, so when you get this line, the top side is your runoff, but the bottom side is your infiltration. Okay, so you have to do this step by step and calculate excess rainfall. What is excess rainfall? Above Horton method. Let's say here you have something like this. Okay, so the top side is your runoff, which is making flow at the surface, and the bottom side is infiltration, which is not our problem anymore. We are taking it out into considerations. Okay, then we are looking at the basin parameters. We should draw basin boundary and find the basin parameters, because we are going to use synthetic unit hydrograph approach. We are going to find the unit hydrograph of the catchment area or basin. And using the unit hydrograph, we will decide what will be the design, what will be the flow in different time steps. Okay, so synthetic unit hydrograph will be used. This is the approach. So you have to know what kind of parameters are used in synthetic unit hydrograph. Okay, so we see that in the synthetic unit hydrograph approach, if you have a basin like this, and you have a river inside, this is the river maybe inside, okay, in the SCS method, there are a number of parameters that you need to know. You need to measure from the basin. One of them is curve number you need. On the other hand, slope of the basin you need. On the other hand, length of the basin you need. Okay, so we have to use that in those informations. Of course, the area is another parameter. So now, in this case, you should calculate what is the curve number of this area, what is the slope of this, and what is the length of the main channel up to high mountains. Okay, since your basin area is relatively small, the time steps of unit hydrograph should be delta T of unit hydrograph. You can take it as 0.5 hours. It's not necessary to be whole numbers like 1 hour, 2 hours, 3 hours, but it could be half an hour. And then in this case, unit hydrograph, the depth of runoff must be 1 centimeter. So whenever you are getting, this is another important information. Since the unit hydrograph, in the unit hydrograph approach, depth of excess rainfall is always 1 centimeter. Whenever you are getting a here unit hydrograph, it will be good to calculate the area under the curve so that you can check if it is 1 centimeter or not. Because if it is not 1 centimeter, in this case, this means that it's not a unit hydrograph. Because for every unit hydrograph, depth of runoff should be 1 centimeter. You know that every unit hydrograph is also defined with T. This T is the duration of rainfall. Okay, so you will assume that it's like a box. Okay, so if you calculate the area, it should be 1 centimeter. Okay, and 1 centimeter excess rainfall is obtained in T hours. So this T is unit hydrograph T. If this 1 centimeter excess rainfall is coming in 1 hour, we call it unit hydrograph 1. If it is coming in half an hour, we call it unit hydrograph 0.5. And it goes like this. Okay, so once you get the unit hydrograph, you know that even we have done some examples. Unit hydrograph is used to convert this excess rainfall into runoff. Okay, so if you define these, let's say the depth here will be d1. Depth here means area. Okay, because remember the unit of I is millimeter per hour. Okay, but unit of T is hour. In this case, the depth here will be in millimeter. D1 will be in millimeter, but be careful, we are using 1 centimeter. So you should convert the millimeter D1 into centimeter. This is D2, same thing, D3, and D4. This is important because D here is depth of runoff, and as you understand from the name, it is depth. It's a height, depth of runoff. Okay, so after you obtain, you use heatograph and your unit hydrograph, you can actually get direct runoff. Okay, direct runoff can now be obtained. How you are going to get direct runoff? It will be like in this figure here. Okay, everything above the blue line gives you runoff. But this runoff is coming to the surface, and at the exit we are measuring flow. So when we are measuring flow, actually the flow usually goes to peak and then goes back to zero. Now it is discharge versus time. Discharge. Okay. So, and then my concern is finding this Q peak discharge. And I'm going to design the culvert according to peak discharge. But in my particular problem, before the culvert location, there is a reservoir. So this reservoir actually helps me to reduce the peak discharge because the water will flow into this reservoir. It will be stored in the reservoir, then it will be given by the reservoir. This is important case. And we have to look at the flood routing, which is your next topic in hydrology. Do you have any question at this point?
No, hocam.
Excuse me, Hocam.
Yes.
When you're doing the synthetic unit hydrograph, are we going to take TR as 0.5 hours?
Excuse me, I couldn't get it. In the synthetic unit hydrograph,
It's like we have a formula for finding TP, which is TR over 2 and plus TL. So I'm going to take the TR as 0.5 hours because I told us use DT as 0.5.
When you are using a CS method in the hydrograph generation and finding the unit hydrograph, one of the important parameters is TR, because when we say unit hydrograph, actually when we are defining a unit hydrograph, we define it with a T value. Unit hydrograph 1, unit hydrograph 2, unit hydrograph 0.5, whatever it is. Here, if your heatograph time steps are 1 hour, okay, as you see here, if your time steps are 1 hour, in this case, you need unit hydrograph 1 to use, because what you are going to say, direct runoff is equal to, you will say, unit hydrograph D1 unit hydrograph 1. Actually, we are going to write an equation like this. Direct runoff is equal to D1. D is the depth of runoff on top of Horton infiltration line, you are going to find the area that will be D1. Unit hydrograph 1, because this step is 1 hour. Then you are going to say 1 hour lag, because the second block is happening after 1 hour, after this hour. So 1 hour later, in other words, 1 hour lag means 1 hour later, I have D2 unit hydrograph 1. 1 because it is going from 1 to 2, it's 1 hour. And D2 is the area of the second block above infiltration line. Here in this example or in this project, you are using it, you are calculating it using Horton. I don't know if I answer your question, Donald. So here, if you need unit hydrograph 1, in this case, what you should do, you should consider in the SCS method, there is a parameter TR. TR is rainfall duration. So you have to take this as 1 hour if you need unit hydrograph 1. But if you need unit hydrograph 2, TR should be taken as 2. If you need unit hydrograph 0.5, in this case, TR should be 0.5. This means that a rain event, 1 centimeter, this means that 1 centimeter excess rainfall is happening. This is intensity versus time. This is happening in, if TR is 1, it's happening in 1 hour. If TR is 2, 1 centimeter depth of rainfall, excess rainfall is happening in 2 hours, it means, because it is affecting your unit hydrograph. Is it okay? Did I answer your question?
Yes, we can. Thank you.
Okay, thank you. Okay, so let me stop here.